Alright, next thing I want to talk to you guys about is orbit. So satellites and orbit and all that kind of stuff kind of go hand in hand. But I want to start with a fairly famous thought experiment, which if we pictured this to be the Earth, and there is a big hill on the Earth, okay? And on that hill there was a cannon. So I know this just got really weird. Okay, big cannon up there, and this particular cannon had the ability to shoot objects at different velocities. Okay, well, at a small velocity, what will happen is that cannonball will come out and will gradually just fall to the ground. Okay, but if we cranked up the force that the gun can apply and shoot it with a greater velocity, it'll travel further before it hits the ground. Okay, so theoretically, there's going to be a point where if I get the velocity great enough, I can shoot it so that it will constantly go all the way around the Earth and come back and hit the other end of the cannon. Okay, that is actually known as orbit. Okay, so when we send a satellite out into space, we have to get it up to a certain velocity so that it is in constant free fall around the Earth. Okay, and how is that done? Well, generally, if we were to look at a section of the Earth, a very slight curve, and I did not draw this to scale. Okay, it turns out that for every 8,000 meters horizontally, the Earth drops off by about 5 meters. It's got a natural curve to it. Well, 5 meters is approximately a 1-second drop. So if you can travel about 8,000 meters per second, you can then stay in orbit. Okay. That turns out to be around 2,700 kilometers per hour. So you got to be moving pretty fast in order to do that. Now, if you go less than 8,000 meters per second, you come crashing down to the Earth. Okay, now this is what happens with certain satellites that, say, run into something. If there's a collision of satellites and things like that, then they can lose some of that velocity. Then they tend to fall back to Earth. Okay, but you're technically, when you're up there, you're not really weightless per se, because gravity still acts on you up there, but you have apparent weightlessness. Because you are in constant free fall, you always appear to be weightless. So when you see pictures of astronauts and things like that, it's not like gravity is gone. It's just that they're falling constantly around the Earth. Okay. Now, if you, say, wanted to go fast enough to get off of a planet, you have to achieve something called escape velocity. Okay. There is a formula for it. I'm not going to go through the derivation of it. It does require us to talk about energy, which we haven't gotten to yet. Okay, but this is the general formula, and I like to put a little ESC on there. This is the velocity to escape a planet is equal to the square root of 2 times g. That's the universal constant. This is always the mass of the object you're on. Like, say, Earth. If you wanted to leave the Earth, this would also then be the radius of the object you're on. Okay, and what's important to understand about that is, technically, it doesn't matter what the size of the object is. Okay, if you want to get a space shuttle off out of our gravitational attraction, you have to travel at a certain velocity, and it's regardless of the mass of the object. You need the mass of the planet that you're trying to escape and the radius of the planet. Doesn't matter that it's a shuttle. So to get a mouse off of the planet, it takes the same velocity. To get a shuttle off it, to get I don't know, maybe Poo Poo Panda off of it. Okay, any object to escape is only dictated by the mass of the planet that you're on and the radius of that planet. Okay, I thought of another couple values that you might need if you're doing some of your homework. The radius of the moon, if you're curious, 1.74 times 10 to the 4th meters. Also, the distance between the Earth and the Sun, 1.496 times 10 to the 11th meters. Okay, so you might need a couple of those if you're trying any problems. All right, that's all I have for orbit.